Okay, so let's continue from the problem that we were doing in last class, right? Okay, so basically we were trying to slow down, right, a supersonic flow down to a subsonic speed using two ways. One is just pass it straight down a normal shock. Another is a combination of an oblique and normal shock. So just to kind of, I'll just, we started off, so this was our normal shock, right? So this was our normal shock. Okay, so here we go. So, right, so what we got was, so we had a flow which was this, right? And what we got here was nearly 5, okay, was nearly 0.5 mark. We got that, 0.4752 to be precise, okay, and we got a ratio of the total pressures. So basically this is region 2 and this is region 1, okay. We got this ratio to be 0.33 actually, okay, 3283, okay. So this is what we got. Let's say it is just around. Okay, so 0.3. Okay, so this is what we got, okay, using the normal, just passing the flow through a normal shock. Now the next thing we did was we passed it through a combination of oblique and normal shocks. So first off we had this, okay, so we had an oblique shock, okay. Okay, so then we had the incoming flow, okay. So again this is 3, this is region 1, then that deflects, okay, and this is M2, right, we did that, and then we pass this across a normal shock. Okay, and this is M3. So what we did here, so this is region 2 and this is region 3, right? So, okay, and this shock wave angle was given to us, right? This shock wave angle, this is the beta, which was 40 degrees. Okay, and we calculated M2 to be around 2, it is 1.9 precisely. Okay, so let me just write it like this. Okay, what we are looking to do here, we have slowed it down, but we haven't yet got to the subsonic speeds yet. So, and what we got here, P02 by P01, here the total pressures is around 0.8. So clearly the drop in pressure is much less here than it is here, okay, but here it has been brought down to subsonic speeds, and here it hasn't been subsonic speeds, and we have passed this through a normal shock here, we've passed this through an oblique shock here. So we stopped kind of here, we haven't done this part here. So let's go ahead and continue to do that. Okay, so now what we're going to do is pass it again corresponding but pass it through this normal shock and calculate the properties in region 3. This is our final region, and now we'll find out the properties there. Okay, so let's do that. Let's go to this next space here. So therefore for this normal shock now, the incoming Mach number is around around 2, right? So this is the normal shock. So what it is saying here, so basically for you to look at this now, if you look at this reference frame, okay, this becomes a normal shock, because now this makes an angle 90 degrees, okay, and the flow is perpendicular to it. Okay, so therefore now using this shock, using the normal shock, okay, so so this is the oblique shock. Let's call this, say, shock structure 1, and this is shock structure, say, 2. Okay, so this is oblique and 2 is normal. Okay, so therefore incoming Mach number is around 1.9. Okay, so we will go to the tables. Okay, so using normal shock tables, okay, from the tables, using normal shock tables, okay, what we get is the stagnation, total pressures behind and in front of this normal shock. So essentially we get a ratio for P03 by P02, which comes out to be this, and which is nearly 0.8 actually, which is nearly 0.8, and M3 comes out to be 0.5956, which is nearly 0.6. Okay, nearly 0.6. So let us write that down over here. Okay, so let's not congest this. Okay, so now, so what we have found is that P03 by P02, right, is around, this is also 0.8, and M3 is around 0.6. So this is around 0.6, which is, and here we got around 0.5, here we got around 0.6. So we kind of nearly at the same speed. Okay. Now our job is basically to find out whether this is more viable or this, and why. Okay. So now basically what we need in this particular shock structure is what is the total loss in what is the change in total pressures in 3 compared to 1, isn't it? So for this particular case, so if I have to calculate P03 by P01, okay, if I need to do this, okay, by this time you should have some idea. So what we'll do is, okay, that's just some elementary clever math. Okay, so once you do that, so we've got the values for both of these. P03 by P02 is here. P02 by P01 is what we've calculated earlier, right? And this comes out to be, which is around 0.6, right? Which is around 0.6. So here, okay, so therefore what you can actually see is the here the pressure loss is almost double that of in this particular case, whereas the speeds, okay, are more or less the same, isn't it? If you look at it, the subsonic speeds to which this has been reduced and this has been reduced is almost similar, whereas the pressure drop, okay, the pressure drop in the process for just a single normal shock is almost double than that of this. Okay, so that is essentially the difference in both of these. Okay. So now let us sort of compare the two. If I were to compare this, so this and this, say, so let me compare this. So if I call this, say, case A, right, and this is B, right. So so basically, say P naught exit by P naught exit, and this is entrance, or let me, how do I write this? Okay. Okay, this is region 1, this is for case B, right? And if I for case A, right? So this is what this turns out to be. Okay. So what you see is that the total pressure, right? So if you look at this, the total pressure in the total pressure in terms of in case B, the total pressure in case B right behind, right here, okay, after it has gone through this system of shocks, is basically 76% more than that of the pressure behind the normal shock here in case A, right. So what we can say here is that the total pressure, okay, so the total pressure in for this shock structure, okay, right after it has crossed both these shocks, is, if you look at this here, okay, 76% more than what it is in this case, which is case A. Right. Now, is that a good thing or a bad thing? Okay. Now, what does that sort of mean? Okay. Well, what it means over here, now this total pressure, okay, this total pressure is basically, it gives us an indication, okay, of the total useful work that this can do. Okay. And in this particular case, so whether this is more efficient or this is more efficient is basically going to be decided depending on how much we are losing in terms of the total pressure. And what we can see over here is that we are losing less pressure when it comes to this system of shocks, right. So the loss in total pressure basically gives us an idea about the efficiency of the fluid, the efficiency of the fluid system that you have. So within this particular case, right, since we are losing less pressure less total pressure when it comes to here, to this system, this is more efficient than this. That system is more efficient than this single normal shock. Okay. So yes, okay. Also see, from, if you look at the tables, okay, if you go and sort of scrutinize the tables a little more, right. So if you increase, okay, if you increase the upstream sort of Mach number, right, the total pressure, if you increase the upstream Mach number, the total pressure decreases. Okay. If this Mach number is increased, okay, the total pressure decreases, right, if you go and look at the normal shock tables. So therefore, if you see here, so therefore in this particular case, if you look at this normal shock and if you look at this normal shock, okay, so this is at a higher in the flow, the speed incoming, right, is at Mach 3, here the speed incoming is Mach 2. Right. So therefore, if you look at this, this is going to have a higher pressure decrease compared to this normal shock. So what this oblique shock actually does is that it decreases the it slows down rather the speed of the incoming Mach number into this normal shock. So that is what this oblique shock is actually doing, right? So if I want to keep my total pressures in check, I don't want them to reduce too much, then I have to work with that Mach number. If I can decrease that Mach number, I will have a less reduction in the total pressure, which is what is happening in this particular case. Okay. Okay, yeah, so let us just make a percentage of how much a Mach number is being reduced. Okay, so if you see over here, okay, so here basically, I mean, we said we're going to just slow it down to subsonic speeds. So in this particular case, okay, so the reduction in Mach number, okay, speed reduction I would say. So let's write it over here. Okay, so in this say particular case, so speed drop. Okay, let me write it this way: drop in speed, okay, is equal to, basically it goes from 3 to around 0.5. So this is it. Right, and we take a percentage of that, okay, and that comes out to be 84%, and here it goes from 3 to 0.5956. So I do the same thing here. So here the speed drop, do the same thing here and you get an 80%. So speed. So what you essentially see is that for an almost same slowing down or drop in speed, okay, we have 76% higher total pressure in this case, which is significant. This pressure here is 76% higher than the pressure drop in total pressure in region P2, right. So clearly, obviously, this is a more efficient way of trying to sort of slow down your incoming flow. Okay, so therefore this is more efficient. Okay, so essentially what we kind of we've learned how to look up the charts, okay, what is happening to the total pressures, okay, isentropic flows, how to calculate the various properties, so on and so forth. Now this is kind of an application. Okay, so how you, if you wanted, how you would be actually, so you can, if you look at this, you can actually have a system of shocks, okay, to use it, if the way you want. Okay, so this is kind of using the same knowledge but looking at it in a different way. Okay, so let's do that for a little bit. Let us look at another problem, and we will see how we will be able to use the simple knowledge, okay, which we have acquired so far. Okay, so let's say and we have these systems. We have sort of we encounter these in a lot of practical applications. Nozzle entrances and inlets several times. So we are going to encounter things like this. Okay, so this sort of information comes in handy. Okay, so now we'll do something else. We'll do another sort of problem and see how we're going to go about it. Okay, so it's a simple case of basically we have a wedge. Okay, we have a wedge and it's encountering a shock. Okay, we want to calculate the drag it is causing. So let's see how we're going to go about this. Okay, so essentially, if you have, say, okay, and okay. So then this is theta, okay, and so I'm going to call this length as L, okay, and we have an incoming Mach number, okay, we have this. Okay, so basically we have a wedge like this, okay, a wedge like this. So the Mach number is given, the theta is given. What we need to calculate is the drag coefficient for this wedge, okay, and something else is also given. So this distance is C, okay. Now this theta is given as 15 degrees and the Mach is given as 5, okay. So we basically have this a wedge, and we need to calculate the drag coefficient, okay. What we need understand by drag coefficient. So well, if you would probably know this, I'll just write it. So okay, so this is nothing but this is the drag force, this is the dynamic pressure, and this is the length, okay. So length, or area, or whatever. So this is your coefficient of drag. So how do we sort of go about this? Okay, we know about shocks and normal shocks and oblique shocks and so on and so forth. What do we do? How do we go about this? Okay, so all right. So you can see here that I have a Mach 5 flow, okay, and I have a wedge out here. So I'm going to have a shock. Okay, so I have a supersonic flow coming in when we have a wedge like this. So we will have a shock. So let's draw a shock structure over here. Okay, so let us draw a shock structure over here. Okay, so I think that it is not symmetric, but it should be. Okay, so please bear with me. So basically I have a shock structure like this. Okay, now in this case, so basically what is going to happen, now if you look at, now it's important to look at this body out here. Okay, so if you look at this body, so this wedge out here, it basically has the body. I can define this by 3 straight lines. Okay, I got one straight line there, I got one straight line here, I got one straight line here. Now that kind of helps. Okay, we'll see how. So what we'll do is, let's sort of so therefore there's going to be a pressure distribution, right, all these surfaces. So let me draw that, and let's see if that makes any sense to you. Okay, so say So say, now because of the symmetry, if you look at this surface and this surface, so they're going to have a pressure, it's the same pressure distribution. So if I look at this, so for example, if I look at this, just consider, this surface. Just consider this surface. Okay, forget about this whole picture here. Just consider this surface. Okay, if you look at this, so just look at this particular, just forget about this whole thing. Forget about this whole thing. Just look at this particular surface. Okay, and see that we have a shock wave coming over here. Okay, so there will be a certain pressure distribution over here. Okay, if that is the case, I'm basically going to just draw that pressure distribution like this. Just look at this. Right, and let's call this as, so basically if this region is 1, I'm going to call this as, say, pressure distribution 2, and it will be the same here as well. Okay, it is going to be the same here as well. Like I said, it's a symmetric . Okay, and this is also going to be, so we're going to call, let me call this also as, so this is also P2. Okay, and at the same time we're going to have a pressure over here. I'm going to call this as, say, P1. Okay, P1. Now, basically the point is that this is a body, right? This is a body, and I have a certain pressure distribution on it. Okay, so if I can calculate this pressure distribution, it is sort of it is encountering a Mach 5 flow. So there is a certain pressure distribution on it. I don't know what that is. I don't know how it should be, but this makes sense to me, with or without the shock wave. Okay. So this has a certain pressure distribution, and I need to calculate the coefficient of drag. So drag, okay. So I can always calculate the drag if I can get if I can get some value for this pressure distribution. Okay. In this case, however, it's not that simple, because we might have a shock wave here. So let's go and see how that sort of comes into the play, right? So, like I said, okay. So now let us look at. So if you look at, say, okay, I need to sort of emphasize this. I'm going to emphasize these sides. Okay, so if I have to emphasize this, okay, so just look at this here. So this is essentially okay. So this is it. Now let us look at let us look at this side. Okay, if I were to look at this side, okay. So let me just say that the total force out here. Okay, let me draw this separately. Okay, let me draw this separately. Okay. Okay, so let's do that. Okay, we have that. So this is the surface. Okay, this is the side. This is the side on which we have. This is the side on which we have a pressure distribution of P2. The length is basically L, right? The length is L. So what I'm going to say here is that, let me call this force. Let me call this force as this, right? So this F, I can write this force. I can write as P2 into L. Isn't that right? So P2 into L. So if I were to do that, okay, now if you look at this, okay, now let us get some angles in here. Let us do the geometry. So now we have this theta is something that I know, right? This theta is something that I know. So okay, let me make this a little more clear. Okay, so this is an F which is equal to P2 into L, right? And this is a theta, right? If this is a theta, so therefore this is essentially a, yeah, let's call this as Fx and Fy, you know, makes more sense to me. Okay, let's call this as Fx and Fy. If that is true, okay, so if that is true, let us just write down here. What do you think Fx is? If you look from here, right, Fx is what? Fx is, okay, P2 into L into sine theta, right? So P2 into L into sine theta, right? Because right, so Fx is that, right? So basically, so Fx is P2L and sine theta, right? So okay, and similarly, if I come at this here, okay, if I look at the, so this is for this surface, right? So this I'm writing it as this force, okay, this entire pressure force, I write that as P2L, and I take this horizontal component, which is Fx, comes out to be P2L sine theta. Makes sense? Okay. We're concerned about the drag, which will be in this direction. So that's why I'm concerned about Fx. I'm not going anywhere near Fy. Okay. So this is now this surface. Okay. This is now this surface. If you look at this, okay. So then here too, let's just draw that. Okay. So here also, let's call this as again F. This is also going to be F, and right. So or let us say this is going to be, so let me call this as say F1, you know, compared to that, and this is going to be Fx1 and Fy1, right? Is that right? So therefore, here again, this is my theta, okay? This is my theta, and this is my theta. Is that right? Yeah, I think that's correct. Okay. So if this is true again, so again this F1, again if you look at this here, so this distance is L, right? This total distance is L, and this is P2. So F1 again, okay, F1 again is equal to P2L. Okay. So therefore, again here, Fx1 is P2L sine theta. Okay, so Fx1 is basically P2L sine theta. Okay, so having done that, now let us look at this this side over here. So if I look at that side, okay, so this is the side. Okay, so if you sort of look at this, okay, so now we will do a little bit of geometry over here. So here, of course, there is no clear pangs, so we will have this as the, let me call that, this is, I will be F2. Now this is a side which is, the length of this side is not known to us, unlike L and L over here. So we need to find that out, but that's where we will use this. Okay, so this is essentially, right, this is essentially that. Okay, and this is our L, this is our theta, and this is our C, isn't it? This length is C, this length is L, and this is theta. So therefore we can find out this particular length, isn't it? We can find out this particular length, and that comes out to be, you can see it from here. So this is L sine theta, right? If that is so, then F2 becomes, F2 again becomes P1, right, into 2L sine theta, right, P1 into 2L sine theta. Okay. So that's all we have done. All we did is look at the pressures on the three surfaces, and then we are writing out the forces. So if I do that now, then what we will do here is get the drag. Okay, how do we write the drag now? So drag is basically the total forces in the horizontal direction, in the direction of the free stream. So here now drag, now that comes out to be, okay, so if you look at, but it's important to see here that this these two, this Fx and Fx1 are in this direction, F2 is in the horizontal direction here, right. So what it will be, drag is basically opposite to the free stream, so we will say that it is equal to basically F2 minus Fx and Fx1, isn't it? So which comes out here to be, so 2, say P1 L sine theta minus 2P2 L sine theta. Okay, so this I can write as 2L sine theta, okay, into this. So and here what we have done is we've basically taken care of the direction. So this is pointed in the this is pointed this is basically facing the free stream. Or if you want to write, if you want to be just not do that and keep like consider this as your positive direction, if you want to keep this as your positive direction, then we'll just write this as, this is just a way of writing. So I'll just write this as so let us do this. Okay, the direction should automatically get taken care of. We'll see how. Let's not talk about the direction now. Let's keep it at this. Okay, it's just the same thing. I've just basically put a negative sign over here. So let's keep it this way, and then we'll come back and see whether this relationship is telling us the direction in which the drag is acting. We kind of know that, but let's keep it this way. Okay, so now basically we need to find out the coefficient of drag. Okay, so this CD L, okay, is equal to C by cos theta, isn't it? Because C is L cos theta, so L cos theta. So L is equal to C by cos theta. Okay, now C is the reason we are trying to use C over here, because similar, it is kind of in this particular case analogous to the chord length if you were to have an airfoil. Okay, and this theta is kind of acting as an angle of attack. Okay, and so I'm going to replace that, this L out here. Okay. Okay, L is equal to C by cos theta. So if I do that here, okay, so then CD becomes basically the drag by Q into C, okay, Q into C. So what we get is 2 L is C by cos theta. So then this becomes tan theta, okay. You get that? I replace this L by C by cos theta. So C comes here, so then I get by cos theta, that becomes tan theta. So then we get this. The C and C sort of cancels out over here, right? So it does. So then what we get here is essentially this. Okay, by Q tan theta. Okay, so we get this. All right. So now Q is basically half rho v square. So this is the dynamic pressure. So let's just sort of work around this value Q out here. Okay, let's do some little math and see what we'll get. Okay, so now this Q is the dynamic pressure, which is half rho v square, right? So I'm going to write this rho like so. So let me write this as half, or say rho, okay, basically, okay. Okay, so I'm basically multiplying the whole thing by gamma p. Okay, if I do that, then what I get over here, okay, I take this rho by gamma p, keep the other gamma p in there, v square. So now do you recognize what rho by gamma p is? You remember this one? So then this is nothing but, so basically we introduce the speed of sound, okay, speed of sound. So then, and we have gamma p v square, and again if you see this v by a, this becomes a Mach number, right. So therefore Q I can also write as gamma p, sorry, so half gamma p Mach number, right, Mach number. So therefore I will write my CD, okay, so therefore my CD, okay, is basically 2 into by Q, okay, so by okay. So in this particular case, so this is my QP over here, okay. So if I do that, okay, if I do that in this particular case, so then okay, so this comes out to be 4, okay, 4 tan theta, okay, this is 4 tan theta, okay, then gamma m square okay. Now the question is, so this Q corresponds to the gamma pressure and Mach number, okay. So if I were to, this is the corresponding. So let us say in here, okay. So when I say P2 by P1, let us go back and sort of look at this over here. Okay, so this is my P2 and this is my P1. Okay, so in this case, okay, so therefore in here the dynamic coefficient of pressure is something that we are taking in this particular direction. In this particular direction, the dynamic pressure in this direction. So what we will do is we will consider this direction, which is this P1 and the corresponding Mach number. You know what I mean? So therefore here, what in this particular case, we will take this to be M1 and P1. Okay, so if I do that, then of course you can see, so therefore what I will get here, CD, okay, so CD comes out to be 4 tan theta, okay, by gamma M1 square, okay, P2 by P1 minus 1. So M1 is something that we don't know. We are saying here, okay, is that the flow passes, we have an incoming flow, right? It encounters this wedge out here, which means it is encountering these shock waves. Then it goes past this, and we have a pressure distribution like this. So once it goes past this wedge, this is here that we are looking to find out Mach number and the corresponding pressure. Okay, so basically we have a Mach number. Okay, so Mach number is 5 and theta is equal to 15 degrees. Okay, so using the charts theta beta m relationship, okay, we get a beta in this case of 24.2. So this is the incoming Mach number, which we know theta is given. So therefore we find out the shock wave angle. Okay, so we find out the shock wave angle, this beta, to be 24.2, right? So therefore then we calculate the normal, of course, right, normal component, which comes out to be 2 point, which is nearly 2. Okay, and again from the, so now once we get this, then we calculate corresponding to this Mach number. So corresponding to this we get P2 by P1, right, which comes out to be 4.736, which is nearly 5. Okay, now we take that, so we have here M1 is 5, P2 by P1 is 4.736, and theta is 15. So what we get from here is 0.114, right? So there is no D'Alembert's paradox here. We have a finite CD, okay, and this is essentially called the wave drag. Okay. Okay, so I think we'll stop here, and we'll actually do something a little another interesting problem. Okay, we'll continue this and do another interesting problem where basically we have a flat plate encountering a supersonic flow, and we'll see how that goes. Okay, all right, thank you.